thanks to all of you for coming. And this is a topic that I'm really excited about, taking something I really love, machine learning, and also blending that with my love for front-end and JavaScript development. And so today I just want to tell you all about how you can also start to do that. So my name is Victor Dibia. I'm a research scientist, research engineer with Cloudera Fast Forward Labs. With respect to my background, I have some of my work has cut across computer science, software engineering. I also have some formal training in human-computer interaction. And over the last 4 or 5 years, I spent a lot of my time with applied machine learning. And so a few years ago, I was a research scientist at IBM's T.J. Watson research lab at Yorktown. And I spent a lot of my time there prototyping natural language and natural gesture interaction interfaces. More recently, I tried to spend some time contributing to the community, but in machine learning and in JavaScript. And I serve as a developer expert for machine learning within the Google Developer Expert program. And currently, I'm a research engineer at Cloudera Fast Forward Labs. So that's a little bit about me. Just to also give you a little bit of a background about what we do at Fast Forward Labs. We like to think of ourselves as the bridge between academia and industry. And so as part of that process, every quarter we will release a research report where we'll go through this really comprehensive process of identifying topics from academia that they're at that sweet spot of making the transition from academic research into stuff that our clients can actually use. And so what we'll do is that we'll spend a couple of months researching these topics, and then we'll write reports around them. And in addition to that, we also build interactive prototypes that show like a concrete demonstration of what these technologies could do. And so the slide you see right now is a prototype we built. We released it just a couple of months ago, something called ConvNet Playground. So essentially, if you think of the task of semantic search, essentially given an image, show me all other images that are most similar to this. It's a common problem, and it turns out that you could solve it really efficiently using pre-trained models. But there's still a lot of decisions that the data scientist needs to make. What model do I use? Inception, V3, VG16, what does all of that mean? Even when you select a model, do you use the entire model, or do you just take a small chunk of that model? And so what this prototype does is that it takes results from computations done on about 8 different models, using about 8 different models, sub-models constructed from each model. And it shows you what the result of performance, search performance would look like if you use any of this. And so this is just like a really simple example of what that interface looks like. You select an image, you perform your search, you can see metrics about search score. Not just that, you can select different models, and then you can look at graphs that help you compare all of these. And so if you're interested in this sort of thing, we have like a platform called experiments.fastforwardlabs.com. And these are all open source projects or open source interfaces that you can actually play with. For the rest of our work, we have a subscription service that anyone can also join. And so that's a bit of a background on what I do. And to today's agenda, which is the exciting part, here's what I'm going to go over. So the first thing, I want to give an introduction to ML in the browser. And so I'll start with some terminology just to make sure we're all on the same page. And then I'll give an overview of the Tensorflow.js library. And so it's got 2 APIs, the low-level API for linear algebra, and also the high-level layers API that you'd actually want to use to build complex neural networks. And then finally, I'll look at Handtrack.js. And so Handtrack.js is this JavaScript library for prototyping gesture recognition completely in the browser, which I developed. It's an open source project. And I'll go through how I actually built this thing and made it available. OK, why machine learning in the browser? But before we jump into that, let's review some really simple terminology. And so the first speaker covered a bit of this, but I just want to make sure that, for those who weren't there at that talk, I just want to cover the basics. And so when we talk about artificial intelligence, it's a super broad field. It's really old, dates as far back as the 1950s. And you can think of it as just efforts directed towards making machines intelligent. And there are many ways you can do that. A sub-aspect of that is machine learning, which is algorithms that enable machines independently learn from data. And so this idea is pretty powerful because there are a lot of problem spaces that as software engineers, it's almost impossible to write concrete rules for. And so if we take the classic example of how do we differentiate a cat from a dog, you want to do things like how many legs does it have? If it has 4 legs, it's either a cat or a dog. If it has pointy ears, it's a cat. If it doesn't. And so, but that can really get complex if you have things like multiple orientations, occlusions, and all that sort of thing. And so you want an algorithm that, rather than writing rules, you show it a bunch of examples and it independently learns the right patterns. Examples of these algorithms are things like decision trees, random forests, reinforcement learning, and neural networks. And which brings us to the interesting part, deep learning. And so deep learning is just a special case of machine learning, but here the main algorithm we use are neural networks. To define neural networks, I like to think of them as just a stack of computational units where computation flows from one unit to another, and I'll give you an example. Over the last few years, deep learning has become wildly popular, and there are some reasons for that. One of them is that it's one of the only algorithms where your accuracy scales with data. And so the more data you have, the more likely your model is going to get more accurate, which is a really interesting concept. In addition, over the last 10 years, there's been like a lot of really great advances in neural network algorithms. And so you might have heard of things like ResNet, Inception, that's for image processing. You might have heard of things like BERT for language processing. So all of these things have made neural networks really, really popular. And the other interesting thing about this space is that these algorithms almost always have the best performance for any given task. The next interesting thing that's made this deep learning really interesting is GPUs. And so researchers and industry practitioners have found ways to make neural networks and deep learning algorithms run really, really fast on GPUs. And so for the rest of the talk, whenever I mention AI and machine learning, what I'm actually talking about is deep learning and the supervised form of deep learning. To cover a few more terms that I'll use as the talk progresses, I just want to introduce some terms. So first is input, things like inputs, weights, sum and bias, activation functions, and output. So the diagram you see here is an example of the most simple neural network you ever see. Typically, does anyone know the name for this thing? Yeah? Anyone? Yes? Okay, cool. So it's typically called the perceptron. Is this most simple neural network you'd find. And everything you see here is really easy to understand. So the first thing is you have here your inputs, whatever it is that flows into the network. The next thing you have is that this input is multiplied by some values called weights. All of that is summed, and some constant value is added called the bias. And finally, you pass all of that through an activation function, and then you get your output. The beautiful thing here is that if we select these weights really carefully, and we select the bias really carefully, and we select the right activation function, we can get this set of computation to kind of represent or approximate functions that we are interested in. So it turns out that this really simple neural network you have here could approximate things like an AND function, an OR function, or a XOR function. So the next question in your mind is, how do we select these magical values, the weights, the bias, and the activation function? So for the weights and the bias, you kind of identify this through a process, through the training process. I don't have enough time to go into much detail, but I think you hopefully get a bit of the idea. So this is a very simple version. However, it's probably too simple to solve most of the problems we want to actually solve in real life. And so it turns out that just one very fast way to scale this up is to add a bunch of these things, to stack a lot more of those simple neural networks together. And here, the terminology that you should think of is you have your regular input. For any set of computational units that are between the input and the output, you refer to those things as hidden layers. And essentially, for any set of layers where all inputs from one layer are connected to all inputs from the next layer, you call those things dense layers. And so that's just a set of introductory terminology. And so next, if we think about the languages for machine learning, typically we'll see languages like Python, R, Julia, and MATLAB. occasionally you'll see some really brave and amazing individuals who are actually doing machine learning in these languages, Java, Go, C, or C++. Any one of them here? Okay, some really brave, courageous individuals. And so one thing you notice about these languages are that they're back-end programming languages. They're typically high-performance languages, and they work really well because they support things like multi-threading. They have really fast I/O access. However, is this a real picture of the landscape of languages that developers actually use? And so to learn more about that, I went to the 2019 Stack Overflow survey of 90,000 developers. And they were asked this question: what programming language do you use the most? And here we see that JavaScript is the clear winner. So 67% of people actually focus on JavaScript. Similarly, they asked people if there's a language you don't currently use, which of these languages are you most interested? Do you want to actually learn? And here again, we see a lot of interest in JavaScript. If we look at GitHub, the trend is pretty similar. For the last 10 years, JavaScript repositories have been the most popular repositories. And there's this really interesting article from a couple of years ago where someone literally said that JavaScript is eating the entire world. And so the idea is that on the back end, people are writing JavaScript server applications using Node.js, and on the front end, people are just like, things are just like, JavaScript is just taking over. And so at this point, we know that people love JavaScript. Those who don't use it, they want to use it. And they're using it on the back end, they're using it on the front end. So the idea is, can we take JavaScript and can we merge that with neural networks? And so most of the time when I talk to people, the first thing they're like, oh my God, this is a bad idea. And when they think about that, typically they have a bunch of questions. So the first question is, can I really train a neural network in JavaScript? Can I express ideas like LSTMs, dense layers, convolutional layers? Can I do all of that, but only in JavaScript? And it turns out that yes, you can. And so your path to that is the Tensorflow.js library. It's a library for building and training machine learning models completely in JavaScript. The next question that people would ask is related to speed. And so the first thing is, JavaScript, while it's a relatively fast language, it wasn't really designed for high-performance computing. In addition to that, neural networks tend to be a really compute-intensive operation. And so people wonder, can I actually have fast computation, but all expressed in JavaScript? Again, the answer is yes. And how do you do that? You do that again through Tensorflow.js. On the browser, Tensorflow.js provides acceleration using WebGL. How many of us are familiar with WebGL? Awesome. So WebGL is this really nice standard that allows accelerated graphics computing in the browser. And what it means here, what's relevant here is that it does have access to a GPU. And so if you do have a GPU or a graphics card on that machine, you can WebGL would let you take advantage of that for accelerated computing. And so in the browser, Tensorflow.js takes advantage of that, and you get really fast computational inference or training as you want in the browser. On the back end, you could use TensorFlow with Node.js, and it gets its acceleration by binding directly to the TensorFlow C API. So pretty much similar performance you get from Python, you get that from Node.js on the back end. And the final question is, how much effort is this? And so for many teams, it's a make or break decision. They're worried, we have a machine learning team, and they spent a lot of time building and training models in TensorFlow Python. And so if we want to use JavaScript, what is the effort associated with kind of integrating that to our workflow? And it turns out that not much effort. And so one of the interesting things is that the TensorFlow.js API is similar to the Keras API. So Keras is just a framework for training neural network models. And so if you're familiar with Keras, there's an easy path or transition to actually start building models with TensorFlow.js. The other interesting thing is that if you have models that are already trained in TensorFlow Python, TensorFlow.js provides a converter that allows you to take your pre-trained models and then convert that into a web model format that can be loaded into your JavaScript application. And I'll get to that in a little bit more detail as the talk progresses. And so at this point, I'm thinking, We know that you can do fast computation. We know that the amount of effort to move Tensorflow.js is not that much. Are there other benefits that you can get by actually using Tensorflow.js? And here are my top four reasons. So the first has to do with privacy. Across the talks at the conference this year, it turns out that you probably have heard people talk about data privacy over and over again. And so with running machine learning models in the browser, you get the opportunity to offer a really strong notion of privacy. Most of the time, you find that despite the best intentions of many software companies, despite their efforts to protect data, data breaches always occur. However, with Tensorflow.js, you can offer a different kind of privacy speech. You can say things like, we don't see your data, and it never gets to our servers, as opposed to saying things like, we see your data, but we promise to keep it and keep it safe. And so for most software applications, in order to offer your user a service, you probably need to use their data. Many times, user data is sensitive. And so how about we move the compute to the browser, perform all our computation, offer a service, and the data never gets to the server. The other interesting ideas around machine learning in the browser is related to distribution. And so at this point, I always like to tell a really simple story. About 3 years ago, I had a few friends who wanted to get into machine learning. And their first step was to install TensorFlow, the TensorFlow software library in Python. And many of them just never got into machine learning because they could not install TensorFlow. And so it's a true story, and that used to be a really complex process. However, while things have gotten a lot better, you can do pip install TensorFlow now, you can do conda install TensorFlow. When it comes to deploying machine learning applications to end users, it can still be a really, really complex process. If you do this in the browser, this kind of simplifies that whole workflow. There are no installs, no drivers, no dependency issues. It's as simple as going to a URL and open a web page and everything just works. In addition, if you will deploy your model hosted on NPM, you can actually have all the benefits of model hosting, versioning, and distribution that comes with distributing libraries through NPM. The next has to do with latency. These days, models can be optimized to run really fast, and they can run really fast on mobile and in the browser. And in some use cases, it's actually faster to run your model in the browser rather than send round-trip requests to a server and then render that request back to the user. In addition, for resource-constrained regions like Africa and East Asia, in these regions, you really cannot rely on the internet connectivity there. And so it's a much better user experience to download all of the model locally to the device and then offer a smooth user experience that doesn't depend on constant internet connection. And then finally, the browser is designed for interactive experiences, and machine learning can supercharge that. And I'll show a few examples in a moment. With Tensorflow.js, you can build models on the fly. You can use rich user data available in the browser, the camera sensors as possible. You can retrain existing models, and you can also enable really dynamic behavior. And there are applications for this in ML education, retail, advertising, arts, entertainment, and gaming. So before I proceed, I want to give a few concrete business use cases of how some industries are already using TensorFlow.js. An example is Airbnb, something related to privacy-preserving sensitive content detection. So as part of their user onboarding process, they will ask the user to upload an image. And they have observed that in some cases, users might upload images that contain sensitive content, like their driver's license and other sort of images. And so what they've done here is that they've put in a Tensorflow.js model that right in the browser, it will tell the user, hi, your image contains sensitive content. We haven't seen it, but we can offer the service of telling you that you likely have sensitive content, and you probably should use another photograph. Another interesting library here is NSFW.js, where it allows you, it's a JavaScript library, and it lets you check if an image contains indecent content, nudity, and all of that, but right there in the browser without sending that image or that content to any backend server. Another interesting example I like is a slide from the recently concluded TensorFlow World conference, where a team, Modiface, they had created a JavaScript application with a footprint of about 1.8 megabytes, and it does virtual try-ons in real time. And so this is all integrated into the WhatsApp mini chat. And one thing you should notice is that it works really well, and so the hair color of the lady in the image is changed in real time, and it works as fast as 25 frames per second. So this is a really fantastic example of optimization and performing machine learning in the browser in real time. And some of you might have seen a neural network playground, which was released by the Google Tensorflow.js team, and just lets you interactively learn about how machine learning works for a few data sets and different problems. Okay, so now that we have a pretty good idea of, good examples of Tensorflow.js, when it works, and why you might want to use it, let's dive a little bit more into how you actually get this stuff done. And for that, we'll look through the Tensorflow.js API. And so what can you do with Tensorflow.js? So the first thing you can do is you can author models. And so it means you can compose your models, define how many layers you want, define things like the type of blocks within your model. You can train this model, test it, and perform inference all in JavaScript. And you can do this both on the back end in Node.js, and you can do this in the browser. And so I kind of think of this as something called the online flow. The next thing you can do with Tensorflow.js is that you can import pre-trained models for inference. So you train it with your favorite computer environment, GPU clusters, CPU clusters. You export your model, and then you import it into your JavaScript application. And I like to think of this as the offline flow. So you train offline, you import the model, and then you run inference. And then finally, we have the hybrid flow where you probably train offline, you import the model into your JavaScript application. And then you can also use local data from your environment and then fine-tune that model and make it just a little better. And so that's more like the hybrid flow. So one thing that can be slightly confusing about Tensorflow.js is the fact that it runs in two different environments. And so the first is the browser. Front end is a really resource-constrained environment. And second is Node.js, which is a complete server environment, and you can do a lot more there. So I'll talk a little bit about what these two environments look like. So with the browser, you can import Tensorflow.js in two ways. So the first is that you could import it using a script tag, just like you would do with, let's say, jQuery. And you could also import it using npm. And so you could do npm install Tensorflow.js, and then include that in build frameworks and tools like React and Vue.js. Again, in the browser, acceleration is achieved using WebGL, and tensors are implemented as shader programs. And so that way, if you have a GPU available on that device, all of the computation can be performed on the GPU. The other deployment environment is Node.js, and you install Tensorflow.js using npm install. And so if you want just the CPU version, you use npm install tfjs node. And if you have a GPU, you do npm install tfjs node GPU. The only caveat here is that right now, similar to the Python API, it will only take advantage of CUDA-enabled GPU cores. And so if your GPU is not an NVIDIA or CUDA-enabled core, you probably can use it. And then for acceleration, it just provides bindings to the low-level TensorFlow C binary. And so that way you get fairly similar performance to what you get from Python. So this is an overall picture of the Tensorflow.js ecosystem. At the bottom, we have Node.js and the browser, which is the two main deployment environments. And on top of that, we have the two APIs that it supports, the low-level ops API and the layers API. And so for the rest of the talk, I'll walk through three examples. The first is how you can use the low-level ops API to fit a polynomial function. And so if you have a polynomial function, how can we create like a low-level optimizer to learn what that function looks like? The second thing I'll talk about is how we can build a two-layer autoencoder, which is a type of neural network in the browser. And while preparing for this talk, I kind of spent some time building an interesting demo that kind of shows out this idea, which I'm really excited to show you guys. And then finally, how can we take a model that's been trained offline and then import that and then use that in JavaScript? Okay, so with regards to the low-level ops API, my suggestion is that you use with caution and only use it if you really know what you're doing. And so let's consider this use case. We have a function, a polynomial function, f of x is equal to ax squared plus bx plus c. And in this case, we want to learn the parameters a, b, and c. So how are we going to go ahead and implement that in Tensorflow.js? So the first thing we want to do is we want to import our Tensorflow.js library. We want to also specify the variables we're interested in learning, their parameters, and here we define them as tensors. We initialize them with a value of 0.1. And then we express the function. A is f of x is equal to ax squared plus bx plus c. And this is what the API's syntax looks like. The next thing we want to do is, given our data, we want to find ways to automatically identify a loss, which is like the difference between what our model predicts and the actual ground truth label. So we create a loss function, which is based on mean squared error. So we get the difference between the subtraction of the predictions and the actual label. We square that and we compute the mean. And then we create an optimizer, which is just a function to tell, to give some signal about how to update our parameters as training progresses. And then we run all of this through a given number of epochs. And the good thing is that each time we call optimizer.minimize, it kind of updates the parameters we're interested in learning. And so that's a really fast overview of the Layers API, of the low-level ops API. So the next thing we're going to talk about really fast is the high-level Layers API. So two things is the recommended APIs for building neural networks, and it's really similar in spirit to the Keras library. So for those who haven't used Keras, Keras is this really well-designed API for composing and training neural networks. And so it gives a really nice way to think about, the components in your network, and a really great way to express those components in actual code. Okay, so to illustrate the API, I'd like us to walk through the process of building something called an autoencoder. So an autoencoder is a neural network that has two parts. Typically, it's being used for dimensionality reduction. And a use case is that imagine that we have an input and it's 15 variables, and we want to compress that into just two variables that represent all of that all of the input 15 variables. So there are two parts. The first part of the neural network is called an encoder. It takes the high dimensions, 15, and its goal is to output two values, which is called the bottleneck. And the other requirement here is that it should learn a meaningful compression such that we can also extract or compute the original input just from that bottleneck representation. And so that's exactly what the decoder part of the neural network does. It takes this input, it takes this bottleneck that has been generated by the encoder, and it learns to reconstruct the original input from that bottleneck. And so one interesting thing is that this whole model, this autoencoder, has been applied for the task of anomaly detection. So the goal here is that if we have some normal data, and we can learn this mapping from input to bottleneck, small dimension, then from small dimension to output. If we train this on a normal data set, that means every time we feed in some new data and we perform a decoding, we get an output, then we should get about the same thing. And so how is this relevant to anomaly detection? And so if we train on normal data, we get our output that's similar to the inputs. Whenever we have an anomaly, a data set that this model has never seen, if it goes into the network and we try to reconstruct the output, we'll get something that's really, really different. And that's called high reconstruction error. And depending on the size of this error of reconstruction, we can then flag stuff as anomalies or not. And so the idea is, if we have normal data, let's say, if we have normal data, we have like an error of 0.8, and if we have abnormal data, we have an error of 0.2, or the vice versa. And we can set some kind of threshold where we say when the reconstruction error is beyond this level, then we flag this data as an anomaly. So how do we express all of this in JavaScript? So if you recall, we have an input layer, which is 15 units. We have a hidden layer. We have an input. We pass it through a dense layer that's 15 units. We pass that through another dense layer that's 7 units. We have a bottleneck layer, which is 2 units. And then that composes our encoder. And then just like other parts is our decoder. To express this in code, we specify our inputs. And on the left, if we're going to use TensorFlow Python in Keras, that's exactly how we'll do it. Input is equals shape. We specify a number of features. The interesting thing that it's almost a one-on-one conversion if we do that in Tensorflow.js. And so to specify our next layer, we have a 15-unit dense layer. This is exactly how we'll do it in Python on the left, and this is how we'll do it in JavaScript on the right. And so we can see it's almost a one-on-one mapping again. We have, as opposed to just using dens in Python, we have tf.layer as the dens. We specify units, and we specify our activation function. Similarly, our next layer, a 15-layer dense unit, very, very similar between Keras and Python. And then finally, a bottleneck layer, which we refer to as Z here, which we also add to our model. So the other interesting thing is that in Python Keras, we can easily do something called a model.summary, and it kind of prints out all of the configuration of a model. The exact same method is available in JavaScript, and that way you can compare if what you have in JavaScript is really equivalent to what you've built, let's say, in Python or Keras. And this is a really useful tool. And so as part of this, as part of preparing for this talk, I built something called an anomaly detection model. And so the data set here is examples of heart rate HCG signals. And the idea is that we have some normal signals, and then we also have a bunch of abnormal signals. And so the normal signals are in gray, are in blue, and the abnormal signals are in gray. And so here we have some labels for our trained data. We also have our test data where we don't have any labels. And then the goal is that right in the browser, we can train a model such that at test time, when we select a specific signal, it can tell us if this signal is actually normal or it's likely abnormal. In addition to that, because the browser is super interactive, we can do things like plot histograms of the reconstruction error. And what you see here is that abnormal data has a reconstruction error that's mostly between 1 and 1.04. And normal data has a reconstruction error that's between 0.95 and 1. And if we put a threshold right at the 1 mark, then we can easily separate normal from abnormal. And we can also visualize the parameters learned in the bottleneck layer. And the goal is that we want to see that there's linearly separatable differences between our normal data and the abnormal data. So with regards to speed, I did some benchmarking. So how fast is inference in Python, in Node.js, and in the browser, and how fast is training in Python, in Node.js, and in the browser. And so what we have here is that I trained 2,600 data points for a total cycle of 20 epochs. And we can see that Keras Python has the best performance for training time. It's about 1.3 seconds. The next best performance comes from Node.js, which is Node, but JavaScript, but using the C bindings. And then finally, it takes the longest time in the browser. So this is not exactly, this is completely unexpected. The surprising, interesting part was that when it was time for inference, I ran inference on 500 data points. We see that Keras Python backend has pretty okay runtime. TensorFlow.js Node takes even more time. But then the browser has the best performance. And so one thing, this is probably surprising to all of you, but there's a good explanation for this. And so I ran all of these benchmarks on my MacBook computer. And so it turns out that my MacBook computer actually has a GPU, a graphics card. However, it's not a CUDA-enabled graphics card. And so what that means is that backend TensorFlow is unable to take advantage of that. But in the browser, using WebGL, we're able to accelerate that computing, and that's why we have faster inference in the browser. Of course, if I had a CUDA-enabled machine, it would probably be much faster on the back end. OK, so this is the last section of this talk. And essentially, I'm going to walk you guys through Handtrack.js. So what is Handtrack.js? Handtrack.js is pretty simple. Given an image, predict the location, the bounding box of all hands that exist in this image. Underneath, it uses a convolutional neural network for object detection. And all of this is bundled into a JavaScript library that allows any developer to actually just import the library and write in the browser without any installation. They can actually start tracking the location of hands in an image. And it's also open source. And so what does that look like? The only thing you need to do is you need to import the library. And so it's hosted on JS Deliver. Turns out that if you have your model deployed on NPM, you can get access to that. The JS Deliver, which is a content delivery network, will automatically serve your assets. And so the only thing you need to do is you need to load the model. Once it's loaded, you can call the detect method, and then it will return a JSON object that contains the location of hands in that image. And so this is what the results of that call looks like. So you get bounding box XY, the width and the height, the name of the class, which is hand, and also some confidence value that says, I'm 0.5% confident there's a hand at this location, or 0.9% confident there's a hand at this location. So how did I build this? And so it's the typical process, machine learning process. We start with collecting some data. We train the model. In this case, I use the TensorFlow object detection API. And then you convert that model into the web model format using the TensorFlow converter, and then bundle that into a web application. So starting with data assembly, I started with a data set called Ego Hands. And so this data set has, it's about 4,600 images of hands, human hands from the egocentric viewpoint. So someone had put on a Google Glass video device and had recorded a bunch of examples of people performing different activities while looking down towards their hands. And so all I did was that I wrote some code that converted the original labels, which were polygons, converted those into bounding boxes, and then exported that into TensorFlow, the TF records format required by TensorFlow for training models. And so the first step is to convert your images into the TensorFlow records format. For each image, there's some metadata, the list of bounding boxes and labels. I trained this using the TensorFlow object detection API, and so it's just a collection of code that just makes it a little easier to perform transfer learning for the task of object detection. It's an open source project, and so I really recommend you to look it up if you're interested in object detection problems. And so because this was going to run in the browser, I selected MobileNet SSD, which is one of the fastest models available for object detection. And once I had all of this trained, I trained this using a cloud GPU cluster. Once I had all of this done, I exported the results of the resultant model as a saved model. The next step was to find a way to get this model into TensorFlow.js, and for that, I used the TensorFlow.js converter. And so to use that converter, all you need to do is to install it in Python, pip install TensorFlow.js. And then you can run the TensorFlow.js converter command from the command line. And you need to supply things like the location of the model, the input format, the output format. The good thing here is that if you have, it supports different TensorFlow formats. And so if you have your model trained in Keras, you can import that you can import that. If you also want to use models from TensorFlow Hub, you could also do that. At the end of this process, the exported model is about 18.5 megabytes. And so in web terms, this is really, really huge. But in neural network terms, this is really small. And so these are one of the trade-offs that you probably want to make. So one of the things that the converter does is that it shards your models into files with a maximum size of 4.2 megabytes just to make it easier to load on the web. And at the end of the process, I bundled all of this into an NPM library. It's hosted on NPM. And the good part here is that for libraries you host on NPM, you can do things like versioning. You can serve it over a CDN, JS delivery. And so it's something that's definitely recommended. And so here, I'll just show some examples of what people have built with Handtrack.js. And so this is an interactive exploration for looking through the chemistry molecules. This is a library someone built called Jama.js, where they had used Handtrack.js to prototype pinch and zoom kind of interactions, but using the entire human hand. And this is a really simple application I built where you have a web server website open, and you can control a ping pong game just by waving your hand in front of the camera. So this is actually on CodePen. If you want to go there, pop it open, you can actually play this game. Yeah. And so here's the part where I do the thing that you're not supposed to do. You do a live demo. Let's see. And by the way, you can always try it out. It's something that's out there. So this is a simple React application. And so all that's happening here is each time I click an image, the model looks at the content of the image, and it draws a bounding box around the location of hands. And so for each of these, and you could do things like vary the confidence threshold. And so what this just says is that each time there's a prediction, if the prediction is less than 0.5, if the confidence is less than 0.5, don't render that box. And so if you really move things down, it will start to find hands where they're not. And if you move it to the bottom, it finds hands where nothing exists. But if you can find that sweet spot where you can have like really confident hands. You can do the same here. And the thing you learn here is that machine learning models are probabilistic. There's always a confidence level attached, and it's always a good idea to visually communicate that. OK, so let's make it a little more complex. Can we spin up video and track hands? And so you can actually see that the model is actually looking at the feed for my camera. And in real time, as I move my hands around, you can actually see it actually following and actually tracking that really well. And so a simple example is that you could actually connect this as a method of interaction. And if I wave my hands, I could actually control this little game I have here. And it all runs in real time, about 20 frames per second. You don't have to take my word for it. You could just go to the website and actually try it. OK, so another model demo I want to show real fast, and this is something that I probably release within the next month or so, is a simple interactive experience where you could build an autoencoder. So in this case, you can add a couple of additional layers. Essentially, here we have an encoder with 12 units, 10 units, 5 units, 3 units, and another 3 units. And you can compile that model. All of this is happening in the browser, and you can actually train it. And so if we click train, we can actually see that we are learning to reconstruct input data. And we actually see that as optimization progresses, we can see the loss or the errors kind of go down. The second interactive graph you have here is a graph of mean square error. So what it just says is that as the model has begun to train, its reconstruction error for normal data is right, the histogram we see on the left, and its reconstruction error for normal data is the histogram we see on the right. And typically, if we set a threshold that's right at this point, we can very easily distinguish real from abnormal data. And once we have this model trained, we can go back to our data and say, for this data set for this data point I have here, tell me if it's normal or abnormal. And for this data point I have here, tell me if it's normal or abnormal. To give some additional background, the data I have here is from a data set called ECG 5000. So it's just an example of about 3,000 discretized recorded heart rate signals, and they're all labeled as either normal or having some kind of defect or issues. And you could train an autoencoder that learns to kind of like tell these things apart. Okay, so right now I've talked about all the beautiful things. TensorFlow.js is amazing, it works really well, but there are some challenges. So the first challenge you need to think about is memory management. And so TensorFlow.js implements tensors as WebGL textures. The implication of this is that you need to explicitly manage your tensors. So if you don't delete them explicitly, your application will just keep on hogging memory. The second thing is that the browser is limited, it's single-threaded, and compute-heavy operations block the UI. You need to think about this all the time. There's device fragmentation. Some devices have CPUs, some don't have GPUs. And sometimes, if your device goes into low power mode, it will disable GPU, and so you can get wildly different performance. So some good practices. Try to spend some time optimizing your model. It might mean that, if you compose your model, you might want to stay away from some compute-heavy operations like full 2D convolutions and replace that, let's say, with depthwise convolutions. You want to remove post-processing from your model graph. You want to explore model compression approaches like quantization, distillation, and pruning. And you also want to look at AutoML or neural architecture search, because this can find really efficient, energy efficient, and fast architectures automatically. Other good practices, learn to use asynchronous methods. That way you kind of avoid blocking the UI thread completely. Visually communicate model load and inference latency. Wherever possible, communicate any uncertainty associated with predictions. The Chrome profiler is your friend. That's one great way to kind of see if your application is hogging up more and more memory. And then for more examples on how to design human-centered AI products, I kind of recommend the Google Pair People Plus AI guidebook. And so to conclude, here are the key takeaways. Machine learning in the browser, it's really interesting, and it's actually attractive if your use case has to do with privacy. If you want easy distribution, low latency, and interactivity. How do you get there? You get there using TensorFlow.js. It provides an API for ML in JavaScript, and it supports these three interesting flows, online, offline, and hybrid. In addition to it, it can be fast. There's acceleration in the browser and also bindings with the low-level C++ API. It's expressive, and it actually plays well with the rest of the TensorFlow ecosystem. And then finally, research advances in compression, distillation, pruning. These things make models run really fast. In addition, there's some new standards that enable accelerated computation in the web. So I think these two things come together to make this space extremely exciting. So thank you. If you want to look at the source code for Handtrack.js, this is a link to it. Happy to take any questions.
Thank you, Victor. That was awesome. We have 2 minutes for questions. Is there anyone who has one they'd like to pose?
Hi, thanks for a great talk. While it's pretty clear that there are obviously lots of benefits of inference phase with TensorFlow.js.
Right.
At the same time, when you think about this online training mode and using TensorFlow for training in browser, do you feel like we're ready? What's your impression there? Are the limitations of confines of a browser is where we are with this right now?
Yeah, so that's a really great question. For really large models, for large data sets, you probably do not want to train all of that in the browser. And so from my experience and from looking at the industry right now, the most popular flow is what I refer to as the offline flow. So what most people would do is that they'll train their models using their GPU clusters or whatever hardware acceleration is available to them. And once they have it at an accuracy level that they're really comfortable with. They'd spend more time doing optimization, essentially bringing down the footprint of that model, and then finally convert that and perform inference in the browser. So I tend to see more of that, and then the next best thing to that is you train the model, you quantize it, you compress it, you optimize it, you import into the browser, and then maybe in the browser you could use user data to kind of fine-tune it. And so that's not an extremely expensive operation, but those are the two ways in which people are actually solving this problem or getting this done. In the demo I showed you, you could actually train the autoencoder from scratch, but what I showed right now was about 2,000 data points. Each data point is 140 variables. So it's not an extremely large data set, but it's possible. But if you're looking at images, things become a lot more complicated and definitely not recommended for training.
All right, that's all we have time for. Thank you, Victor. Appreciate it.
Thank you.